Okay, hey everyone, welcome back to class. As a reminder, things we did last time, we started working on the particle in the box problem where we're restricting our space from 0 to L. We found a wave function associated with that, normalized. We found the energy associated with each of those wave functions, so each scion has some En associated with it. And n can be any counting number from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up. We tried to find the x values, so I put x sub value. It's kind of one of the unfortunate things is how do you label x values versus the variable x. So I'll usually put subscript value or something like that on there. And we said that we can't really figure that out because the wave functions we're using are not eigenfunctions of the position operator. So we said, okay, let's not worry about that. Let's find the average position. We said the average position is just going to be the middle of the box because the wave functions we have are symmetric from one end of the box to the other. So we ended up with an average position that was independent of which wave function we were using. The particles on average are always in the middle of the box. What did change from wave function to wave function was this idea of variance. How much did that average, how much did the probability spread out? And so we found some cases, we found the case where it depends on this n value, where as the n value changes, how much that spread of probability changes, even though the middle of the box is always the same. So we did all of that, and we said, okay, there's a couple other things we can still do. We didn't have time to do any of the momentum stuff. So that's what we're going to do today. We're going to do the momentum stuff. There's going to be a couple weird asides of like, oh, this is interesting, we'll use it in the future type ideas. We may get to doing multi-dimensional particles, but we might do something else. So let's go ahead. As a reminder, we have the momentum operator, negative I h bar d by dx. It's a Hermitian operator on purpose. That's why we've got that negative I out front. Our average value would just be the integral over I all space, psi star px psi d tau, assuming psi's are normalized. And then we can also get the variance of that the same way we got the variance of x. We're going to take the average value of the momentum squared minus the average value of momentum then squared. Right? So those two are different things, and we'll see if they're. We found when we did that for position, these two values were different. We'll see if that's also true for momentum. A lot of this is going to work out pretty quickly. I'm nervous about class today because I don't know how fast this is all going to go. It might go really fast because once we start getting good at these integrals, they don't take nearly as long as they did for the first few classes. There's a bunch of places where we start to recognize things. We're like, oh, that's the thing that was 0 already. That's going to be 0. So let's see what happens. Let's start with just calculating the average momentum. So we're just going to calculate the average momentum. And again, we can do some classical analogy here, even though you know it's not going to really work. You got a particle in a box. Which direction is it moving? If it's moving back and forth, a lot of you are pointing back and forth. If it's moving back and forth, what's the average momentum? Is it just as if it's moving that way just as much as moving that way? If it's moving back and forth, ends up being 0 momentum. So we're expecting the average momentum to be 0, and we're expecting eigenvalues of a positive momentum and a negative momentum. Let's do one thing at a time. Let's calculate the average first. We have this expectation, average momentum. I'm just going to take this. I'm going to start plugging things in. We've got our 2 over L integral. We got 2 over L integral of sine n pi over L x star negative I h bar d by dx on sine n pi over Lx dx. So again, I'm putting extra parentheses here just to kind of create a visual parallel between our generic equation. I've got psi star p hat psi. This part, the derivative part, we're going to go ahead and put through. This is going to be a little bit interesting. Derivative sign is cosine. So I'm going to have, that negative hangs out, that negative does hang out, that negative does hang out. So we're going to have negative IH bar n pi over L cosine n pi over L x. Notice for our expectation values, this is the operation we would do to find our expectation values, and we're in trouble. We get a different function back. We'll have to deal with that in a little bit, but let's finish average first. So my average here is going to be, I'm going to move this whole mess out. So I get a negative IH bar n pi over L times 2 over L integral sine n pi over Lx cosine n pi over Lx dx on the bounds from 0 to L. Integral tables. This whole thing, do you have your integral tables? Grab them, double check my work. If I'm doing this right, this ends up being negative cosine squared n pi over Lx divided by 2n pi over L on the bounds from 0 to out. Double check me. I wrote this down yesterday. Always double check me. This is the sine cosine integrals. Also handy for you to be comfortable with your integral tables. Recognize which integrals we're using more often and less often. So if you need them on homework or quizzes or exams, they're easy to find. Is it sine squared? I
might be wrong. I think I'm wrong.
I'm hearing cosines. Where did I bring my integral tables? I didn't bring my integral tables. I'll use the integrals in the back of the book. Cosines? Okay, here we go. Always double check, always a good idea. The trigonometric ones above the periodic table. We've got sine, cosine, negative cosine squared over 2a. Yep. Okay. Great. So it's negative cosine squared. The negative sign makes me happy because I didn't want a negative sign, so the negative and the negative eliminate each other. The fact that I have an I kind of makes me anxious until I go and apply these boundaries. What if I plug in L here and I have the cosine squared of n pi? What's the cosine of n pi? Show me with your fingers. Cosine of pi, or 2 pi, or 4 pi, or 5 pi, or 6 pi. Not 0. 1. Cosine of pi is 1. Okay. So we can do cosine of pi is 1, cosine and 1 squared is 1. So we're going to end up with a negative 1 with a bunch of constants divided by 2n pi over L, minus, if I plug in 0, cosine of 0, also 1. So I'm going to have a negative 1 over 2n pi over L. 1 minus negative 1? 0. Right? Those two negatives become a positive, and so it's minus 1 plus 1. You factor out the 2n pi's don't really matter. You can factor all that out. We get 0. So this means our simple thinking that we did earlier, px equals 0, our average momentum, because this is a particle, well, there's two options here. We already did the interesting option. What's the boring option? Average momentum is 0. No particle, nothing moving. Right? What if we did this for nothing? Right? That would be boring. You'd have no momentum. The only way you have no momentum for a particle in a box is if you have no energy, which means it doesn't exist. That would be like a null answer. That would be like nothing exists, we're not looking at anything. That would be boring. The other option is we've got that particle bouncing back and forth inside the box. So we can go ahead and plug in our px, our average momentum, is 0. Now, the way that we show that this is a particle bouncing back and forth inside of the box is interesting and hopefully not too confusing. We have one problem, and then we have a way to fix that problem. Right? The first problem is p hat on sine, let's just plug it, n pi over L x would be negative I h bar n pi over L cosine n pi over L x. Why is that a problem? Same thing we saw for position. Right? The way we would say this is sine functions are not eigenfunctions of the momentum operator. Sine functions are not eigenfunctions of the momentum operator. We take the derivative of sine, we get something else. So there must be some other way. The options are we can't say anything about the individual momentums, or we can do something that's kind of more fun, which is we can take our function and we can rewrite it. This is akin to taking your XYZ coordinate system and switching it to r theta phi. Right? Hopefully we haven't done that in this class, but hopefully you've seen problems like that in other classes where it turns out like if you're doing gravity, doing it in XYZ is kind of a bummer. So sometimes we switch it to r theta phi, and it makes the problems easier to solve. That changing the coordinate system sometimes makes the problems easier to solve. What we can do, and we can think about this two different ways. The first thing we can think of is linear combinations are allowed. So if we have a linear combination of a solution, that's also going to be a solution. Things we looked at before. So as example, if sine kx is a solution, and cosine kx is a solution, then we can have a combination of sine kx plus cosine kx is a solution. So if we kind of remember when we first started doing this problem back when we were first looking at particle in a box, before we normalized it, before we solved everything, we said sine functions would work, cosine functions would work, exponentials e to the I kx's would work. So we can take linear combinations, we can add those things together in different proportions and make different answers. To do it in different proportions, I didn't give myself enough space here. Let me give myself a little bit more space. To give ourselves different proportions, we might put a coefficient 1 and a coefficient 2 in front. To say, I've got this sine function behaving more in my answer, I've got this cosine function behaving more in my answer. This works because we are learning, so, and I should say this is a solution. I've got another thing that I want to add in. Oh, it's up here that I want to put it. That part that I've been saying, where I've been Hermitian and linear operators, this is where the linear part comes in. Right, so essentially, if I wanted to do an example of how this works, I'm going to take like the momentum operator, but I'm just going to try to simplify it. I'm just going to do d by dx on some function where my function is like c1 psi1 plus c2 psi2, where this is the generic form, but this is like sine is my psi1, cosine is my psi2, and I'm going to apply this. And so the thing we want to see is if I do d by dx on c1 sine n pi, sine kx, trying to keep it generic, plus c2 cosine kx, that's the same as doing d by dx on c1 sine kx plus d by dx on c2 cosine kx. Now, for most of us, we're like, yeah, of course, you can distribute a derivative. In this class, pretty much all the operators we're going to use are linear operators. There are a couple examples of non-linear operators. That would be like square the thing, right? If you had this thing squared, it's different. If you did sine kx plus cosine kx squared, that's not the same as sine squared plus cosine squared. So there are some examples of non-linear operators. We're really not going to worry about them too much this quarter. If any come up, we'll get scared and we'll make sure we recognize that they're non-linear and we'll not use them. Because now the second postulate of quantum mechanics says for every observable in classical mechanics, there is a quantum operator that is a linear Hermitian operator. So our operators, when we're using them, should be linear and Hermitian. Okay. So why are we doing this? Well, okay, so doing these linear combinations are going to do a couple things for us, right? This is essentially, like I mentioned, this is like taking our answer in sine cosine space. This is just changing it around to the same thing again. What we want to think about is how could we come up with a function that is an eigenfunction, let's write this down real quick, an eigenfunction of the Hamiltonian and an eigenfunction of the momentum. Remembering the Hamiltonian is just 1 over 2m px hat squared. So I want a function where I take the first derivative, and it's pretty much the same as taking the second derivative. Sine doesn't do that, cosine doesn't do that, but e to the ix will do that, or e to the x, e to the ax, e to the constant x. So we can, with that in mind, we can change our functions around, and we can come up with a new way to write this, right? Taking a linear combination of solutions and finding a different way to write this. Kind of like taking our x, y, and turning it into r theta, right? Just changing which functions we're using to represent which things. I'm going to erase this stuff. I'm going to leave that stuff for a moment. Okay? Questions before I do any erasing? So there's a couple different ways we can think about this. And this is a really nice tool, this rewriting things as linear combinations. We're not going to do it too much right now, but this rewriting things as linear combinations, we're going to be doing this when we go to multi-electron systems. We're going to do this when we're looking at hydrogen atoms or helium atoms. We're going to take our functions, we're going to add them together. This can be really done, thought about in terms of a Taylor series expansion, or where one function by itself might not be a good answer, but if you have like 6 functions added together, it gets you closer to the right answer. And then you can change the proportionality out front for how much of each of those functions you need to get something that looks like a good answer. We'll do this in the practical world. We do this a lot of the time where we've got measurements of a system. We're trying to model the system. we've got these parameters we can wiggle around to try and model the system and explain what's happening in the system. But what we're going to do first is we're going to try to rewrite this. So I'm going to rewrite this as a linear combination. My psi is going to be a C1 e to the ikx plus a C2 e to the minus ikx. Let me plug in what k is for us. Let's just leave, no, let's plug it in. Right, for us, that k is n pi over L. The reason I'm tempted to leave it as k is because I'm just writing down more variables. None of them matter. They're all kind of the same thing. But I wanted to have parallels with our sine functions. So that's why I'm writing down the extras. So I've got these two things. Those coefficients out front, we've got to figure those out. There's a couple different ways we can go about this. So the first thing we want to notice is that if I take the first derivative of e to the I n pi over, oh, that's not a nice way to write that. E to the I n pi over Lx versus taking the second derivative this will get us e to the I, this will get us an n pi over L, this will get us I n pi over L, e to the I n pi over Lx. This will get us an I n pi over L squared, e to the I n pi over Lx. Right, and the point of this is, whether we're doing the first derivative or the second derivative, that means these exponential functions are eigenvalues of momentum and of energy. Which means they're going to be a little bit nicer to work with if we want to know things about momentum. So why didn't we use them the entire time? Well, we could have, right? These functions are, these were a viable solution. And it turns out they're not just a viable solution, they are the same thing. So it turns out that there is, where'd I put that other paper? Oh, I left it someplace. There is a way where we can rewrite these things as each other, where if you just have a sine theta, you can rewrite that as 1 over 2I e to the I theta minus e to the minus I theta. We can go through the proof of this if you really want to. I'm going to encourage you to do it at home. You should do it at home. Do it at home. Right? It turns out that you can rewrite sine theta and cosine theta as Taylor series expansions. And then you can write e to the I theta as a Taylor series expansion. And it turns out they're all related to each other. Right? Sine is the odd part, cosine is the even part, e to the I theta is both parts together. So we could go through that. I left my notes for that someplace. I'm flipping through this being like, where did I put that? I think I know where it is, but I don't have it with me. I could go through it if you really wanted to, but again, do it at home, do some Taylor series expansions. It turns out that we can rewrite sine of theta as imaginary exponentials. These imaginary exponentials are like oscillating sine parts. That's the way it works out. That's the way the math works out. So when we take this, we can take our sine function and we can rewrite it in terms of two exponentials, this e to the I n pi over Lx and this e to the minus I n pi over Lx. And we're essentially just saying, look, this is the same thing. Question?
Can we also write cosine theta?
Yeah, it turns out we can also write cosine theta like that. It comes out a little bit different. I have to think about this now. Okay, let me think about this I feel like pausing the video for this, but I'm not going to. Let's see if I can remember. I can't believe I don't have this written down with me. I know I've got it someplace. I've got it for sine. There, that's what I want. Okay. So you can have e to the IAX. This is the way that I always do it. E to the IAX is equal to cosine AX plus I sine AX. And e to the minus IAX is equal to cosine AX minus I sine AX. And so I remember, this is the one that I usually remember. I wanted to make sure I didn't get it wrong. So you can see if I add these two things together, I get 2 cosine. So if I add these things together, I get 2 cosine. And so if I do cosine theta would be equal to 1/2 e to the IAX plus e to the minus IAX. If I subtract these from each other, I'm going to get I sine theta plus I sine theta. The cosines are going to subtract off. So I'm going to get 2I sine theta, so I divide by 2I. That just gets me sine theta. Again, we can prove these relationships with Taylor series expansions. In my opinion, it's like my favorite thing to do with Taylor series expansions. Because it just blows my mind that this works. That you can rewrite sines as exponential. No one showed me this until I took a quantum chemistry class in my undergrad. The fact that you could write down sines as exponential terms and cosines as imaginary exponentials and cosines as imaginary exponentials. The reason you'll see it till now is, when is it useful? Now. What makes it useful is this sine function. So why we didn't use those exponential functions to begin with, why I didn't use this as the thing we started with, it turns out it would have worked, right? These things are equivalent to each other. The boundary conditions are way harder to do with this function. Like if you wanted to do your 0 boundary condition and your L boundary condition, with this, we'd also have to do the smoothness, right? We just had to do like it's 0 at the edges. With this one, you also have to do the derivatives are constant. So the derivative at 0 is the derivative at the edge is also 0. And you end up, it just ends up being more difficult. There are places where we have to do that. When we look at tunneling phenomena, we have to use the exponentials. Because the math with this, well, technically we don't. It's just then the math with the sine functions is way too difficult. Right? So it's just a matter of picking which set of functions we're using depending on what makes the math easier. Just like you could do electric fields in the XYZ coordinate system, but it turns out it's easier if you do it in the r theta phi coordinate system because electric fields are radially dependent. Same thing here, we're just changing which functions, the way we write the functions to make the math easier. Now, what this does for us, I'm going to erase this bit over here. Questions before I do about any of this stuff? What this does for us is it allows us to change, right? Taking this linear combination, I'm essentially saying I've got 2 bits, these 2 bits. Solving for C1 and C2, there's ways we're going to do that in the future. Right now, we can just do it through this rewriting process. These 2 bits essentially end up giving us root 2 over L sine n pi over Lx becomes root 2 over L times 1 over 2I e to the ikx minus 1 over 2I e to the minus ikx. So what this has done is we've got our normalization constant. We now have, we probably need to renormalize this because we've got these extra features here, but we've got our coefficients up front, and it's essentially, we can factor out that I, and this is essentially saying half of it is this e to the ikx, half of it is this e to the ikx, right? It's half and half of those two functions. So now that we're using this function, we can go ahead and just do, I can just kind of look at this one part. Oh, I put kx's instead of n pi's again. I'm mixing up my notations. I want to be consistent. I'm keeping it all as n pi's. N pi over Lx, n pi over Lx. Okay. Same thing, that's the definition of k for us, but again, I'm just trying to be consistent so all the notation on the boards is the same right now. So my px is going to be, I'm just going to apply it to this e part here. I'm going to have applied to e to the I n pi over Lx. That will give us, I actually already wrote this down over here. This gives us, ooh, I didn't actually write this down properly. This is going to be negative I h bar d by dx of e to the I n pi over Lx. The reason I didn't do it completely is I need my expectation values, my eigenvalues to be real. And notice up here, my function's not real. I've got these imaginary bits all over the place. But when I take this operation on it, the i's are going to end up canceling each other out. And I'm going to get an I times a minus I, which is just equal to 1. So I'm going to get h bar n pi over L e to the I n pi over Lx. So operator on a function returns a value and that same function back. Eigenvalue problem. This essentially corresponds to a particle moving from the 0 side over towards the L side, right? A particle moving one direction. Guess what's going to happen with this other bit? It's the particle going the other direction. If I do px hat on e to the minus I n pi over Lx, I'm going to kind of skip. You end up getting the same thing, just a negative sign. So you end up with the particle. So this is the particle moving towards L. This is the particle moving away from L. We get the particle moving in two directions. Average value of the particle moving in two directions, still 0. Question?
Why do we ignore the 1 over 2i in
the 1 over 2i, because it's just constants, right? So essentially, actually, I should say, in both of these, I need to multiply a bunch of extra things, right? I need the 1 over 2i, I need the square root of 2l. There's a couple other constants I need in there. The main thing I wanted to show, I'm not calculating the exact value of what's going on here. I'm just showing you that it kind of corresponds to a particle moving one direction and the other direction.
Okay, so the eigenvalue wouldn't just be the part that you highlighted. It would be all of.
Yes. We would have to, let me think about this. I think I thought about this earlier and I was like, oh yeah, you would still have to do, I think you would still want to calculate like so I think the thing that's messing it up, the reason, if I did this thing overall, since I'm doing just the little pieces to kind of show, like I'm not doing, I should be clear, I'm not doing the expectation value for this entire, or the eigenvalue for this entire function. I'm just showing what's the expectation value for this bit and this bit to show that it's a particle kind of moving in both directions, right? So I'm not doing the eigenvalue for this whole thing. I'm just saying if I imagine this is one function, this is the other function, my particle is moving both directions. If we did it for this entire function, I think everything would end up canceling out because you'd have the particle moving both directions. You'd end up with this bit plus this bit, and you'd end up with a 0 for your overall momentum. because it's moving both directions, your momentum's going to cancel out, just like the average value. I think we should probably do it as homework. Try it out. See if it works out the way I think it does. Mm-hmm.
You said the top p value is moving towards L, and then like the other side, like the bottom p value is direction.
Yeah, so essentially, we got a positive momentum and a negative momentum. Positive momentum is going towards L, negative momentum is going away from L. The total momentum, if we add up the momentum of the particle, if we add up the momentum of both bits, we should get a 0 momentum, and our average momentum should be 0. But we can come up with this conceptual way to understand that there is actually non-zero momentum occurring. It just totals up to 0 eventually. Okay. Let's try another thing. What about the variance of P? Right, this sigma px squared. So a lot of the math we've done is actually going to be, right, this d by dx squared is going to come in because the Hamiltonian is a px squared. So a lot of the math we've already done, we're just going to kind of repeat. Some bits we already know, right? Since this average value is equal to 0, the average of momentum squared, 0 squared is just 0. The only part we have to do is this px squared bit. But the math is going to look really similar to things we've already done. And we're going to get values that should look familiar. I think I can even fit it into this bottom bit here. So we're going to go ahead, we're going to calculate So we're going to calculate the sigma px squared to see how much the momentum, average momentum of 0. But the momentum for the different wave functions should be different, right? Since momentum corresponds to energy, like it's all kinetic energy, there's no potential. If our n value goes up, our momentum should go up. And so I think there should be some n dependence someplace. So that's why I'm going to check the variance. I'm going to say, okay, well, I think each wave function should vary away from that average of 0. Let's take a look at what happens. Again, I'm going to focus on just calculating this px squared average, which is generically going to be the integral over all space of psi star px hat squared psi d tau. Plugging in the bits for us specifically, that would give us integral from 0 to L. Is that too small? I'm looking for the people way far away. It's a little bit too small. I'll write it a little bit bigger. I'm just really close to the board. So it's huge to me. Integral from 0 to L. We're going to have our sign. I'm also going to switch back to using the signs. Why am I switching back to using the signs instead of this definition of this sign of like these two things added together? Because I only want to do like 1 multiplication, not 4 multiplications and 2 derivatives. Right? It's just going to make the math a little bit easier again. And since they're equivalent, it should be okay. And how do I know to make that choice? Right? This is the part that usually frustrates students, is like, how do I know to make that choice? Because once I sat in your seat and a teacher made me do it the hard way. So if you're doing the homework has you do it with the exponential terms instead of the sine terms. And it takes a really long time and you're like, wow, I got the same answer. But, you know, or you could just, you know. I mean, for me, this kind of looks obvious. Tell me if this doesn't look obvious. If I put e to the I n pi over x plus e to the I n pi x, and then I took the second derivative of e to the I n pi x, e to the I n pi x, I would have to FOIL all of that. I would end up with 4 different integrals to do. It just sounds harder than using sine. Question?
Why did we switch them from the sine to...
So the whole reason I switched to using this was to show this idea that we could, so there were 2 important things. One, the idea that we could change which functions we're using. In the future, we'll call that changing our basis set to make the math easier, depending on what properties we're looking at. Right? For looking at energy, changing that doesn't help us at all. it was just as easy to use sine as it is to use e to the in pi's. When we looked at momentum, it turned out that if we just used the sine functions, we couldn't get this idea of individual eigenvalues associated with the momentum. So we switched our basis because we're like, oh, I do want to figure out something about momentum, and I can't do that with the sine functions. So I'm going to switch to the exponential functions to figure something out about momentum. But for momentum squared, for p hat squared, sine functions just work just as well because second derivative of sine is sine again. So I recognized that this was going to be easier in this case. And so I was like, okay, in that case, I'm going to make that choice, the mathematical choice, just to make the math a bit easier. So it's kind of just looking at what do we want to know and which mathematical functions are going to let us say something, which mathematical functions are not. In the future, and again, this is something we're going to use a lot in the future when we're looking at multi-electron systems. We're going to find out, writing things with the different functions is going to make things easier or harder. Places where you might be familiar with this already, hybrid orbitals are linear combinations of atomic orbitals, right? It's the s plus the p plus the p to get an sp2. That's linear combinations of functions. Also, when we do molecular orbitals, when we're talking about electrons across multiple atoms, we'll run into the same thing where it's going to be the 1s on this atom plus the 1s on this atom to make an overall function. So this idea of linear combinations is going to be something we use a lot in the future.
Sorry, another question?
Sure, yeah.
So for the p-value that we solved, don't we have to incorporate the 1/2i into it? Or no?
Yeah, so for this p-value, I was doing it for the individual pieces rather than this overall function, because I wanted to kind of look at, can I say something about the momentum of the particle in different bits rather than looking at the overall momentum. The overall momentum is still backwards and forwards added together. It's like these two values added together. The overall momentum still ends up being 0, but it's actually, we can imagine it's because it's moving back and forth. Not because its momentum is 0, but because its momentum is equally backwards and forwards. Okay, so again, switching back to sine because it's mathematically easier. We get sine n pi over Lx star negative I h bar d by dx squared on sine n pi over Lx dx. And I'll have, how do I want to do this? I'm going to do something a little bit weird. I'm going to leave my root 2's over L's inside here. That's a weird root. Right? So normally I collect them and bring them all the way out. It's fine if you want to do that. I know another nice thing that's going to come up here. So when I do this IH bar d by dx bit, negative I squared is negative 1, so that's going to give me negative h bar squared. D by dx squared on this is going to give me an n squared pi squared over L squared. Taking the derivative, sine goes to cosine, cosine goes to negative sine. So I'm going to get times negative root 2 over L sine n pi over Lx. The negatives cancel out, that's great. This is going to get me to, now this is where it is going to be nice. And I made a funny choice here. Oh, let's see here. H bar squared, n squared, pi squared over L squared, integral psi star psi dx. So notice I left this root 2 over L, so that's just my psi. I left this root 2 over L with that, so it's just psi. What's the integral of psi star What's the integral of psi star psi if it's a normalized function? That's 1. Right? That's why I made that funny choice of keeping those root 2's with it, because I knew, since it was normalized, if I took those root 2's out, I would have just gotten an integral that was L over 2, and the L over 2 and the 2 over L would have canceled. But leaving things as normalized functions, this is the benefit of recognizing normalized functions. When we recognize normalized functions, we're going to have a bunch of integrals where I'm not going to do that integral anymore. I know it's equal to 1. Question?
Right after n squared pi squared over l squared, is that an x?
No, that's a multiplied by. Because I messed up with that negative sign. I didn't move the negative sign out yet, so that is like a times. So it's n squared pi squared over L squared times negative root 2 over L sine n pi x over L. The negative comes out with this negative to make it so this thing ends up all the way positive. And then we've got that bit. Other question?
Yeah. And why don't we just like do 2 over l sine squared n pi l x?
We could have, but then this integral would have just given us an L over 2, and it would have gotten us the same answer. Right? And I can show that. If I erase this bit, I can show you that in more steps if you'd like. More steps? Are we okay? I think we're mostly okay. I'm getting very little. Okay. Point is, we've got something interesting over here. And we're going to talk about what these two things mean together. So we're going to have h bar squared pi squared over L squared. Yeah. L squared, let me make sure I've got this all right. N squared. Okay, here's the cool part. I don't know how many more things I want to do today, but oof, there's so much we could do. So much we could do. So here's the interesting part. This deviation with respect to x gets worse as the box gets bigger. Right? It's proportional to L. If the box is bigger, we know less and less about the position. If the box gets smaller, we know more and more about position. The opposite is true for momentum. For momentum, as the box gets bigger, we have less and less variance with momentum. So a big box, we can say something about the momentum. The momentum is kind of like traveling the entire time. As the box gets smaller, particles bouncing more in our classical analogy. The particle would bounce more, and we're going to have a higher deviation in our momentum. So it's directly proportional. Our deviation with respect to position is directly proportional to the size of the box. Our deviation with respect to momentum is inversely proportional to the box. The same thing is true for the n. It's inversely proportional to n. It's directly proportional to n. Again, with the variance of the standard deviation of position, there's a minimum associated with that as n gets really small. Same thing with momentum. There's a minimum that we have. As we get to really large values, that changes. Now, what we can do is we can put these two ideas together, right? When you see this depends on 1 over L squared, depends on L squared, there's a natural choice to make, which is just multiply the two together. That will get rid of the dependence on the box. So if we multiply the two together, I'm going to move this back over here now. So if we multiply the two together, we end up getting sigma x squared, sigma p squared is equal to, that L part ends up canceling out. With a little bit of rearrangement, we get an h bar squared over 4, n squared pi squared over 3 minus 2. So that's a lot of rearrangement, but you can notice they've got the n squared pi squares in common, so if I factor that out, If I factor that out of the momentum part, it's going to leave it behind for the other. There's some mathematical rearrangements I did to get from these two multiplied to each other to get to this. But that's the eventual equation we get. And what this tells us is there's a minimum uncertainty. As n gets to the smallest possible value, this doesn't go to 0. As n gets really, really large, sure, it gets really big. But as n goes to the smallest possible value, n equals 1, this uncertainty of position and momentum is not 0. This is Heisenberg's uncertainty principle. Well, one version of it. 1 through 5, you've heard of Heisenberg's uncertainty principle. I've got little bits to lots of bits. Essentially what this says is we can't perfectly know position and momentum at the same time. And this is something that blows people's minds when you think about it in terms of classical physics. Because the whole point of classical physics is you're measuring the position and the momentum of something. So the whole point is you're measuring the position and the momentum. You can know both things. In quantum mechanics, so this idea that you can't know the position and the momentum, that there's always a minimum uncertainty of knowing both things, really bothers people. In the quantum world, where we've already got some uncertainty, some variance, some distribution in our positions, and some deviation in our position, in our momentums, and some deviation in our positions, this is less kind of mind-blowing. But it does mean that there is some limit on how well we can know position and momentum at the same time. And it's particularly position and momentum, because if you remember the first day, or just remember physics, position and momentum are related to each other. Momentum is how quick the position is changing. So it makes sense that these two things relate to each other. And on the quantum scale, measuring one messes up the other. Did you have a question?
Yeah, could you explain why the deviations for x are indirectly proportional to n?
You've got this 1 over n squared term. So I don't have a classical explanation for that. It was just when we went through the math, we ended up with 1 over n squared from the integrals we did. So we've got this inverse n squared dependence. That means as n gets really, really small, we're subtracting off a smaller bit. And as n gets really small, we're subtracting off a bigger bit. And so that's going to be lower variance when we're looking at the small n's versus bigger variance when we're looking at the large n's. And the opposite's true for momentum.
But if you're subtracting off a bigger bit, then wouldn't it?
Yeah, am I getting that wrong? If you're subtracting off a bigger bit, no, because you're subtracting off the bigger bit, so your overall variance is smaller. Is that what I said twice? Did I say the same thing twice, or did I say different things twice? Watch the video, tell me if I said it wrong. So, right, subtracting off a bigger bit means this overall value is going to be smaller. Okay. Question here in the back.
So as n gets bigger, the more we know about position is what you're trying to, a particle in the box.
As n gets bigger, we're subtracting off a smaller. So I wouldn't say the more we know. I would say the smaller the deviation is.
Okay. Yeah. And then is that?
Wait, no. As n gets bigger, hold on. Let me make sure I'm not messing this up now. As n gets bigger, we're subtracting off a smaller thing. So no, we're subtracting off a smaller bit, so the variance gets bigger as n gets bigger. Because it's an inverse subtraction relationship.
Gotcha.
That's the same for momentum.
Yeah, because it's not subtracting. So as n gets bigger, we kind of know less about both. And the thing that was messing me up, and I hope I didn't say it wrong earlier, it's not just an inverse, it's an inverse subtraction. It's too many things to think about at once. I have to be really careful, and hopefully you all see how careful I have to be, and I have to slowly think through it. So take your time as you're thinking through these ideas. Be really careful. Was there another question?
Yeah.
Question here, then over there.
The same as Ethan's. I think it's just like clarifying what deviation means. Like, if
So-
something has a bigger deviation, do we know
So-
more or less about that value, or no?
It's more we know. So it's we know the average value is always the middle of the box, and then it's how much does our distribution spread from that average value. And so if we have, so average value is always the middle of the box. If we've got a big variance, big deviation, that spread is going to be really large. And if it's small, it's going to be really small. There's still some spread. It's never a zero spread. So it's a smaller spread or a bigger spread. So does that tell us anything about, like, does that say how well we know the value? Well, if you've got a small variance, you know the range of values a little bit better versus a large variance. So there's something you can say about, like, well, we know less values are possible or more values are possible, but it doesn't really let us say much more than that. Other question? Yeah.
So just to clarify, so as L gets bigger, that means there's bigger deviation.
So for which one we're looking at?
So for the X.
If we're looking at this deviation of position, it is directly proportional to L. So a bigger box, so the particle is essentially, its position is going to spread out to fill the whole box. So I should draw a sine function. So if we look at the, n equals 1, we end up with a sine function kind of like that. That's a terrible drawing of a sine function. But if the box gets bigger, this function is the same shape and it just gets spread out more and more and more. So that spread, that variance gets bigger as the box gets bigger because the function still looks the same. It still arcs in the same way, but it just gets bigger.
And then the smaller the n is, the bigger the value you're subtracting, which makes the variance smaller.
Yes. The smaller the n, the smaller fractions are bigger numbers, and so we're subtracting bigger numbers, which means smaller variance. The other way, if you remember the computer modeling I did last time, as the n value got big, we had like a lot of wiggles, and it looked like the particle was smeared everywhere. So for me, the visuals really help. So looking at the pictures in the book, doing some programming with MATLAB, so you can make your own functions. We'll do some of that pretty soon. Question?
Wait, n is the amount of energy in the system?
N is depending on, so n is a counting number. It does directly relate to the amount of energy in the system. So we've got different possible functions with different possible n values. And those n values directly correspond to, well, n squared corresponds to the energy in the system as well. So yeah, those things all relate to each other. Other questions? Okay. I'm going to do something. Question? Yeah.
At what point does the Heisenberg uncertainty principle become no longer valid? Which n?
So it's kind of, the thing that bothers people about this uncertainty is not that it gets really big, right? Because we can always make terrible measurements. So no one's really worried about, like, nobody's really worried about how big it can be, because we can always make terrible measurements. The thing that really bothers people is that you can't know things perfectly, right? There's a limit to how accurately you can know something. There's some quantum scale, you just can't know position and momentum at the same time.
So it's no longer, because like classical, right, you definitely can.
You can definitely know both.
The moment you get the quantum, it's like when this.
Yeah, so this classical idea, as we push it smaller and smaller, is like, oh, I can always know where a baseball is. I can know its exact position and its exact momentum. But when you get smaller and smaller, you're like, okay, when you get down to the size of electrons, you can't anymore. And that's where it starts really, and honestly, the accuracy of the measurements we are currently making don't get close to this yet, right? H bar squared, this is 6.626 times 10 to the minus 34 squared. Like, we have to get really accurate for this to happen. So it's really just bothering people on the theoretical scale right now. Question?
I honestly kind of take offense to that a little bit, because you can say, oh, I know the position of this exactly, but even with like any sort of measuring tool, if you look at something, there's always going to be error bars.
Yeah.
So like even
Right.
at the macro scale, you never know like the exact position of something, because no matter what you use to measure it, there's always going to be error.
So this gets to the idea of like, well, how exact is exact? Right, this gets it, and this gets to the philosophical ideas inside of like quantum mechanics of, well, how exact is exact? How precisely can you know the position of a ball? how much does that variance matter?
I guess this would just be like the smallest error bars you've ever seen in existence, because as you get smaller and smaller,
Right.
and you get more and more precise measurements, you can say, okay, we know it's positioned to smaller and smaller error bars, but this is the...
This says there's a limit to how
Yeah.
small your error bars can get, and once you get to this level, your error bars can't get any smaller. And that's what starts to bother people. It's like you can't get. Gets into a big like still philosophical debate about our ability to know information about systems. So that's where it starts to get really kind of philosophical. For us, another way we could get to this idea, I'm going to show you one more thing, and then we're going to do something else. The other way we can get to this idea is we can look at, which order do I do? I don't want to mess this up. We can look at do the two operators we're trying to use commute? Does the order of which I operate, so can I measure position and then momentum, and is that different than measuring momentum then position? Does the order of our measurements matter? Because like in classical physics, the order of measurements never matters. So you can measure position and then momentum, and it seems fine either way. You might have error bars, but you can just get a better measurement system. Here in quantum mechanics, we find that this order starts to matter. And the way we often write this down is x hat p x hat on psi minus p hat. X hat on psi is equal to, and we want to know, is this 0? And it's only 0 if the operators commute, if the order of operation doesn't matter. So I'm gonna stop there because I want to do something else. We'll talk more about this next time. It does get quite conceptual, but we'll talk more about this later.